Everybody here has an interest in weather, I'm sure. And hopefully, like I said earlier, we'll have a chance to learn a little bit about some of the weather that we do get here in Oklahoma and a lot of other places too. All right, let's see if this will play here. And I'm fighting a sinus infection, so I'm sorry if I sound a little nasal, but we'll get through it. Okay, just trying to play. All right. It's taking a while. I just rebooted my computer and now it wants to run really slow. I've got so much video in this thing, it's probably like taking a while to go through. But we do get a lot of severe weather. One of the first graphics I'm going to show you is, there's a lot that comes with severe storms. We've got, let's just name some of the different aspects that we get with severe storms. And it can be any time of year. Obviously, a lot of times it's focused on the spring months. But we can get severe weather any time of year. We've had tornadoes in every month of the year. But what are some of the things that we get that comes with severe weather? We've seen some of this in eastern Oklahoma just within the last day or two. Anybody have anything? Still thinking. Come on, buddy. You get dramatic temperature changes. We've seen that with what we've had. You might be wondering how in the world do you get thunderstorms when the temperature is 29 degrees? And what happens is cold air is very heavy. It's very dense. So it's going to hug the ground. And a lot of times with these Arctic air masses that come in from the north, sometimes they just kind of ooze in underneath really warm and humid air. And that's what we have seen the last couple of days. It's what you call the shallow Arctic air. Think of it as a pool. You have the shallow end of the pool, you have the deep end of the pool. So with shallow air, that cold air is very shallow. You go up about a mile, the temperature can be 55, 60 degrees. Oh, wow. That's what I'm talking about. Now, my computer is still thinking here, so I'm going to escape out of this and try this again. All kinds of computer issues, but that's how that happens. So what's happening, you're getting this warm, pretty humid air going over the top of the really cold air that we have at the surface. So the thunderstorms are developing in that warm air and then raining down in to the cold air where we are. So that's how that can happen. Now you're not going to get tornadoes or anything like that because that cold air would really prevent any circulation or anything like that from reaching the ground. But you can get some pretty good thunderstorms and even sleet, thunder sleet, and if it's cold enough, sometimes you can even get thunder snow. All right. Well, we're going 13 minutes in and my computer's still giving me issues. But at least we got this going here. So stop thinking, buddy. Let's go. But that's what we've seen in the last few days. And again, we haven't had so much flooding here in Bartlesville, but we cover a pretty large area. With Fox 23, we cover all the way down to McAllister. Believe it or not, we have 2 counties in Kansas that are technically under the Tulsa market. Chautauqua County and Montgomery County in Kansas are technically our coverage. All right, looks like we might be up and running now. So it says 10 o'clock, but we'll make it 10:14. Who loves the comic strip The Far Side? One of my favorites here with the front porch forecast. I don't know if you can see the comic here, but rain squalls are coming in. My knee's acting up. I'd say more like a blizzard, judging by my hand here. Well, something's going to happen. There goes my head. So again, we're kind of touching base on this. When spring's dangerous, we just kind of touch base with flash flooding. We're hearing the thunder out there right now with the lightning, tornadoes, one of them as well. Hail. I've got some pretty good hail video I'm going to show you, and of course damaging straight line winds. Out of these, which one do you think is probably the one that is the deadliest?
Lightning.
Flash floods. Yeah, flash floods. So yeah, flash floods on average, 140 deaths per year, and a large percentage of those, not all, a large percentage of those are people trying to drive across flooded roads and things like that. That is unfortunately how, I'd say, I think it's between the numbers are about 60 to 70%. It's a very high number. or a flash flood deaths could be reduced if people just didn't try to push it too much. But lightning on the lower end, tornadoes. Now tornado deaths after about 2011 when we had that unbelievable year, they've actually gone down quite a bit. But it's, again, that's an average. You'll see fluctuations year to year. That's kind of an average. But flash flooding is the #1 unfortunate killer. More than 140 deaths per year. Again, there you go. More than half of all flood-related drownings occur when a vehicle is driven into high water. And I'll show you an example here in just a moment. But 6 inches of fast-moving water can knock you off your feet. 2 feet of water is enough to cause most vehicles to kind of float downstream. Flash flood watches and warnings, they're issued by the local National Weather Service. Here in Bartlesville, we're covered by the Tulsa National Weather Service. If you cross the state line into Sedan, Kansas, or into Coffeyville, or into the other side of Kansas, they fall under the Wichita, Kansas National Weather Service. Here's a video from Chris Novi. This was actually the day of the El Reno tornado, but there was also serious flash flooding that occurred. Let's see if I can get this to play. There we go. But again, it's a perfect example of, whoops, back one. Let me try this again. There we go. So it's a perfect example. You don't know what's underneath you. And just because you think there's a road there, doesn't mean there is. So he's a storm chaser, and this, he pretty much has calmed down his chasing since. He had a pretty nasty experience with this, and you'll see why here in a second. Boom. Oops. He is down in. He got carried underneath the road. He's lucky to be alive. Whoa. So you don't know, just because it looks like there's ground there, the road might be there, it may not be there. So that's why I would say, turn around, don't drown. He's very lucky to be alive. It was a very emotional experience for him, and it definitely had affected his life. He's had kind of a new look on life after that happened. He ended up on the other side of the road, got carried underneath. Pretty crazy stuff. But again, kind of what we just talked about, avoid high water, ravines, ditches where the water's going to kind of funnel down into. Do not swim in, walk around, or drive through flood waters. Turn around, don't drown. And keep an eye on children. I mean, how many of us as a kid, we see this rushing water coming down a creek, we're like, oh, let's throw something in there, watch it, we're running down. Like, I can remember when I was a kid, and my dad coming up and, get your butt in here, because as a child, you're fascinated by this rushing water that's going through the creek. So just, something to keep in mind. Lightning, what to do in case of a lightning strike. If it could only move so fast.
Yeah. But
there really is no safe place in a thunderstorm. Pretty interesting here. Energy from one lightning flash can light a 100-watt light bulb for more than 3 months. Lightning flashes can reach 50,000 degrees Fahrenheit, which is hotter than the surface of the sun. And it forms, as you got these thunderstorms, we kind of got, some thunderstorms going in overhead. Basically, you have different charges. It's the same thing as you're going to open up the door and you get a static shock. Or you're, wanting to fill up the gas tank or just getting in your car or something like that, and you get that static shock. It's the exact same thing, but on a much, much larger scale. So you get the differences in charges here. Negative charge here at the bottom of the thunderstorm, positive charge here on the ground. They start getting closer to each other, drawing to each other, and eventually they make the connection. That's why it's not always the case, but why taller objects tend to be struck the most is because there's a shorter distance between that and the base of the cloud. Again, it doesn't always happen that lightning could easily strike over here, but it's going to look for the path of least resistance and shortest. But it's kind of random. Here's some extreme slow motion lightning. And you can watch how these feeders come down here. It's just randomly going out. Whichever one of these hits the ground, that's where the connection is going to happen. And you can see how random it is. It's getting drawn down. You got, again, a charge coming up from the top. One of those is going to make the connection. Boom, there it is. So this is slowed down, ridiculously slow. Then again, a little bit faster, but you can kind of get the idea. You can see how it comes down. The one that makes the connection is where you see the actual strike occur. And you can see on the next, this is one of my favorite lightning pictures, on the next one here, and you can actually see the process. So here's the one that actually made the connection down to the tree. Here are our step leaders. All these are kind of reaching down, kind of going down, and then you also have upward leaders, which these are very rarely photographed. This guy did an awesome job with his photograph here at this farmhouse. You can see one of the upward leaders right here coming off of this power pole, and there was actually two came off this tree. This is the one that made the connection. There was actually a second one that was coming off.
That was cool.
That's pretty cool. That is really cool. So when lightningers around, stay indoors or in a vehicle. A lot of people think it's the rubber tires of the vehicle that offers the protection. It's not. It's actually the steel cage of the car itself. So if the lightning strikes the car, the bolt, the charge goes around the car and then out the bottom. So you're in this protected cage and the charge goes around you and then will make the connection to the ground. A lot of buildings are unsafe: carports, open garages, covered patios, picnic shelters, beach pavilions, golf shelters, tents of any kinds, baseball dugouts, sheds, greenhouses, things and such. If caught outside with no shelter, the best thing to do is to crouch down in a low position and try to keep your feet together. Because if you have your feet apart, it helps make the connection to the charge if the ground would become charged. So you try to put your feet together and crouch down as low as you possibly can. That's if, worst case scenario, you're caught out and you have nowhere else to go. And if you're caught out in the forest, you're going to find the lowest set of trees to crouch beneath. Again, lightning can strike up to 10 to 20 miles away from the storm. This is what we call a bolt from the blue. You can see the example here to the right. Our thunderstorm is right here. This one comes way out to the right of the storm and strikes, off to the side of the storm, not even in the storm itself. But if you hear thunder, you're close enough to be struck by lightning. The general rule is kind of wait 30 minutes after the last rumble of thunder before venturing back outdoors. And keep an eye to the sky. Towering clouds can indicate that a thunderstorm is developing. Plan ahead and know the forecast. A lot of times in the summer, we'll be out on the lake taking the boats out. You'll start to see these towering clouds building up, and those could eventually become thunderstorms. So just kind of watch for that. Lightning strikes, there's many different ways to get struck. Poor Bob here is having a bad day. He just took a direct lightning strike on the ground. Now there's other ways to get struck. It could be a side flash or side splash standing next to the tree, where you get just a bit of it comes off the tree and gets you. Then the ground current, like I was just talking about, where the lightning strikes the tree, but you actually will get a little current that comes out of the ground. Depending on how far away you are from where that is really going to kind of determines the brunt of the hit that you're going to take. The closer you are, a little bit more of a strike. But that's how you hear groups of people that have been injured, or multiple people killed taking shelter underneath the tree when the tree gets struck. That's kind of how that happens, because the charge will go into the ground as well. And again, there's that ground current. The feet were separated, so it kind of completes the charge through the body. And then conduction. Lightning can strike way over here, but if you're along a fence, any sort of metal fence, if you're touching it, the charge can travel all the way down and get you. The streamer, when we just saw the photos of those upward streamers, they aren't typically as powerful as taking the direct hit, but they pack a little bit of a punch. It'll do some damage to you if you happen to be connected to an upward streamer. And I should have added a photograph. Sometimes you've seen people with their hair standing up before a lightning strike. That's kind of what's happening, is that charge, that upward streamer, kind of getting drawn off the body And if that starts to happen, you want to try to, get down. If you have time to find cover, get in cover. But that can indicate that lightning is about to strike. Hail is another big factor when it comes to severe weather. It does a lot of damage, especially to crops and such. There's an area in northeast Colorado that's called Hail Alley because the amount of hail that they get there every year. I mean, it's just basically go Denver to the north and to the east. But it basically forms, and if you think about the power of a thunderstorm updraft, and we'll go into kind of the dynamics of what makes a thunderstorm, but think about having a hailstone, about this big, solid ice, the power to be able to just float that in the air, how fast the air has to be rising through this thunderstorm, just kind of hover this hailstone before it gets too heavy and big and falls down. When you start getting hailstones this big, to be able to just float that in the air and maneuver it and just float it around in the thunderstorm, the air inside that storm has to be rising at about 100 plus miles an hour. That gives you the idea that the power that these storms have. This here, the largest hailstorm ever recorded, 8-inch diameter, weighed almost 2 pounds. That was in Vivian, South Dakota. And when you get large hailstones, they'll be falling at 100 and 150 miles an hour. So if you get hit in the head, I mean, it could be deadly. And I always try to avoid hail at all costs when I'm chasing. This was a situation where I got too mesmerized, and I'll show you the video here in just a second. This was in Elmer, Oklahoma, back on May 16th of almost 3 years ago now. So we were chasing this supercell. It was coming right across, and a supercell thunderstorm was a rotating thunderstorm. We'll get into that in a second here as well. There was the tornado. We were here. Ideally, when you're chasing, you want to be out in this area or maybe down here. You don't want to be up here, but the road network that we needed to get on, you can see all the other chasers on here as I'm trying to get this to work. The road that we needed to go east on was right here, so we kind of positioned ourselves. And what happened is we got too busy watching this, and typically right in this area is where you're going to get the big hail, and you'll see what happens to us here in a second. Hopefully you can hear that. So there's our inflow cloud. The tornado is going to be right here. It's rain wrapped right now, but you can kind of see the outer edge of it. But we're in a bad position here to get hit with big hail. And if you watch the ground here, you'll start to see some of the big hail dropping.
Absolutely. All right, we're getting some big hail. Let's get out of here. Let's get out of here.
So look at some of these hailstones. They're huge.
That's it.
Massive.
Cow. Big tornado. That's a big tornado.
So we made a mistake getting too close and letting the storm get too close to us instead of just getting east. I always try to avoid hail.
Oh my God.
But
yeah, that's what we're going to do. Oh my God. Oh, I busted my shield. I lost it.
So a lot of people lost windshields on this day. I actually fared pretty good compared to most.
Oh, windshield. Watch your eyes, watch your eyes, watch your eyes. Oh, God.
This is a pretty violent tornado. It actually was only an EF2, I believe. It was only an EF2, but it really didn't really do a lot of damage because it remained pretty much out in open country. This was a pretty violent tornado. I thankfully did not go into a populated area, but I imagine if it would have, it probably would have been rated higher. And this thing was. You can see there's our inflow going right there, right into this area right here. So here was what happened. Again, I fared pretty good compared to most people. But I did have to get my windshield replaced, had to get my headlight replaced, which I didn't even realize until we stopped to fill up with gas on our way back. But a lot of people took more damage than I did. I didn't lose any side windows, thankfully, but there was a lot of chasers that took some damage on that. So tornadoes. This is actually the first tornado I ever witnessed. Evanston, Texas, April 21st of 2007. That's just north of Lubbock. And there's some features that you can actually look at here, which we'll kind of talk about a little bit here in just a moment. With a supercell thunderstorm, you get a rotating updraft. So it's usually in a rain-free area as long as it's not what you call HP, high precipitation. This area here is the RFD, so the air is actually flowing down here. You get this little RFD cut right here, and then this is where the air is rising up into the storm here. So just some features, but the United States is not the only country that actually gets tornadoes. A lot of the world sees tornadoes, and these are what I call some of the hot zones of tornadoes. There's a little tornado alley in South America here, Argentina, and actually I would say it extends all the way up here to around Paraguay, into southern Brazil. You get there, if you look on, do a YouTube search for tornadoes in this area, they get some pretty violent tornadoes in this part. And it's a similar setup, although a much smaller scale to what we have here in the United States. You get the very warm tropical flow coming off the Atlantic Ocean. You get dry air. If you're familiar with the geography here of South America, we've got the Andes Mountains and a lot of high desert dry air out here. So they'll get a little bit of a dry line that sets up like we do as well here in the United States with the Rockies and the desert Southwest. So it's a very similar setup, but on a kind of smaller area that it affects. Europe gets their share of tornadoes as well, Australia, and another hot zone, kind of India, Bangladesh. If you do some research there, they've had some very deadly tornadoes, even deadlier than what we have because of the infrastructure not being quite what we have here in the United States. But what country do you think has the most tornadoes per square mile? It's a trick question. It's not the United States, but there's a reason for that, is because a lot of the western U.S., you don't get a lot of tornadoes per square mile. If you just took Tornado Alley, obviously the U.S. would be number one, but it's actually the United Kingdom. Again, if you took just Tornado Alley without question is the zone across the entire world for tornadoes per square mile. But watches and warnings just kind of explain what some of the differences are. A thunderstorm watch or a tornado watch is issued ahead, usually before thunderstorms actually develop, but in anticipation that we could see severe weather. All watches, every one of them, come from one location, and that is the Storm Prediction Center in Norman. They are in charge of the entire country, issuing any severe thunderstorm and tornado watch. And I would say all watches, that's just severe thunderstorm and tornado watches. Flash flood watches, any sort of winter weather watches come from the local National Weather Service office. Warnings means that a severe thunderstorm is happening or a tornado is happening, or we at least have strong rotation detected by radar. So if a severe thunderstorm warning is issued, the hail has to be at least 1 inch in diameter. Small hail is not considered severe. It has to be at least 1 inch in diameter to be considered a severe storm. The wind has to be at 58 miles per hour or greater. So the wind's blowing around at 50 to 55 miles per hour. It's a strong thunderstorm, but not technically reaching severe levels. And in tornadoes, it's either been sighted or you have strong rotation detected on radar. And all warnings come from your local National Weather Service office. So preparing for a tornado, you may listen to local news or NOAA weather radio, stay informed with any watches or warnings. Make sure you have plenty of batteries and flashlights. Know your community's warning system. Everybody, sometimes there's a lot of confusion because certain communities will have different criteria for blowing the tornado siren. Sometimes it can just be strong winds. So know what your local community does when it comes to that. Prepare for high winds, secure line furniture, trash cans, hanging plants, and pick a safe room where your family members and pets can go during a tornado. We don't have a lot of basements in Oklahoma, but if you've got a basement, that is ideal to try to get to the lowest ground as possible, storm cellar. The idea is if you look at your home, you want to put as many walls between you and the outside as possible. One of the biggest things with tornadoes is not just the wind, it's the flying debris within the tornado. And that can penetrate that first wall, your outside wall. So as many walls as you can put between you and the outside as possible. That's the thing. You'll kind of have to look at your own home and determine what the best room would be. Sometimes it's a bathroom, but sometimes bathrooms aren't necessarily the best because they could be on an outside wall. So it might be a closet or maybe a laundry room, just kind of depends on your particular home. But you may have heard like radar detected circulation or radar detected tornado. What does that mean? So we had a tornado warning. This is Osage County. I pulled this one from a few years ago. So Doppler radar, it's the same thing on a much bigger scale as the police officer with his radar gun taking your speed going down the highway. Much larger scale. So not only can Doppler radar kind of see where rain is falling and where it's most intense, but you can also look at the velocity with what's moving within that rain. So you can see how fast rain might be moving toward the radar, or how fast rain might be moving away from the radar. So when you have a really tight couplet, green's going to, red's going away, usually means we've got pretty tight circulation right there, and that is the area of concern. When it gets really tight, tornado warning will be issued because the National Weather Service will issue the warning. They see that there's tight rotation within the storm. So we don't know if there's a tornado on the ground, but it might be capable of producing one. So let's go ahead and issue the warning in case there is. And that's where spotters really come in handy, because as let me go back here. The radar site, National Weather Service radar site's right near Inola. If anybody's driven along Highway 412 east of Tulsa, you'll see it sitting out there. So what happens, get this back up, because of the curvature of the earth, as the radar beam goes up, it actually gets higher into the sky. So the earth kind of curves, the beam gets higher and higher. So out here, you're hitting much higher into the storm than what you would be if you were like right around the radar. So the circulation's pretty high up into the storm, so we don't have an idea what's going on at the ground, but we know that there's strong circulation. That's where, again, storm spotters can really come in handy. They can report in what they're seeing at the ground. But an idea here, again, this is the Mayflower, Arkansas tornado. There's a reflectivity with what we're looking at as far as rain and everything like that is concerned. So you can see the heavy rain. We've got a little debris ball there, so it's actually picking up pieces of debris that are being wafted up into the storm. Here's our velocity. Green is inbound, red is outbound. I had a professor in college that would say, green on red, get under the bed. So right there we go. There's our tight circulation right there. And now Doppler radars across the country have been upgraded to what we call dual pole. So used to, the wavelength of the Doppler radar was horizontal. Now we've added a vertical wavelength as it goes out. So you can actually kind of get somewhat of a 3D structure of the particles that it's hitting, whether it be raindrops, or in some cases, when you have a tornado, it could be pieces of debris. And depending on the type of return that comes back to the radar, with correlation coefficient, you can kind of depict whether it is meteorological or what it's hitting is non-meteorological. So if you've got this, and then this blue area here, which indicates something non-meteorological that the radar beam is hitting, you put those 2 and 3 together, you have a pretty good idea that maybe the storm was throwing up debris up into the storm, and it certainly was. This was what was the ground truth here. We had a pretty violent tornado on the ground at this time as the debris was getting wafted here. So what to do during a tornado? Again, we touched base on this earlier. Safe place is to be underground. If you can do that, safe room, obviously that's excellent if you've got a safe room. That is, and that actually, some sort of storm shelter, that saved a lot of lives with Moore tornado a few years ago. The timing also helped that a lot of people were out at work, but a lot of people had storm shelters that saved a lot of lives. And it's not possible, again, we kind of talked about this earlier, interior room, lowest level of a sturdy building, as many walls between you and the outside. And one thing to keep in mind too, if you've got a helmet, football helmet, baseball helmet, bicycle helmet, whatever you've got, motorcycle helmet, put it on. You know, protect your head, you know, from any sort of debris or anything like that that could hit you. It's not a bad idea to do that. And again, if you're outside, try to find the nearest sturdy building. If you can't, try to find a ditch or something like that and just lay as low as you possibly can and put your hands over your head. Mobile homes are not safe because they just don't handle the wind very well. So if you live in a mobile home, if you've got neighbors or family, find a place that you can go in case of a tornado threat. After a tornado strikes, I'll try to go through some of these pretty quickly. You know, check for injuries if you're trained with first aid. Help who you can until emergency responders arrive. Continue listening to local news or your NOAA weather radio. One thing to also keep in mind is if there is a tornado threat, put shoes on, good shoes on. You don't want to be walking through tornado debris in sandals. You got nails, glass, all kinds of stuff that can do damage to you. Again, watch for fallen power lines. They might still be active. You don't want to touch a power line and get shocked. Broken gas lines. Report anything to the utility company. Battery powered flashlights, and do not use candles because they can be knocked over and cause fire. Plus, if you have broken gas lines, you got a bigger problem on your hand. You know, clean up spilled medications, bleaches, gasoline, other flammable liquids, so they don't become a fire hazard. Keep your pets and animals under your direct control, and take pictures. If you happen to be hit, make sure you take pictures of the damage of your home or whatever building that you may own for insurance claims. And if you're away from home, only return when authorities say it's safe to do so. But there's a way to measure tornadoes. This is a damage scale. The enhanced Fujita scale is a damage scale, so it can only be measured by the damage it does. And as I talked about with that earlier tornado with Elmer, it was probably a more violent tornado, but it pretty much stayed out in open country. So the damage it did do, you know, was fairly sparse and only got EF2 damage. So it is again a 100% damage scale. Your low-end tornadoes. Let me see if I can get this to pop in here. I'm losing the battery. There we go. Low end 65 to 85 miles per hour, your EF0, 86 to 100 miles an hour, EF1, EF2, 111 to 135, EF3, you're in that 136 to 165 range, EF4, between 166 and 200, and EF5, you know, you're up around 200 miles per hour. And again, you start getting into the EF4s and EF5s, and we're talking less than 1% of the actual tornadoes that occur. Most tornadoes, I'm trying to get this to work, most tornadoes are going to fall in your EF0, EF1, or EF2 range. But again, they can still do some damage, and somebody that gets hit from a low-end tornado, that's still a big deal to them. Thunderstorm stages. As we talked about earlier, you know, you see the towering cumulus go up. In the mature stage of a thunderstorm, you've got both the updraft and then the downdraft, which is where the rain's coming in. And the dissipating stage, the updraft is pretty much cut off, and the rain pretty much takes over and eventually rains itself out. And you have different types of thunderstorms as well. Single cells, these are more of your afternoon type pop-up stuff. They can become severe. You might get some damaging winds out of this, maybe some marginal severe hail, but probably not going to be your high-end severe storms. Same thing with the multi-cell cluster. You can get clusters of storms that kind of pop up. You can see here, we've got a single cell out here, a couple clusters of thunderstorms right here. What can sometimes happen is when one of these storms will die out, the outflow from those storms will kind of create a little boundary, and then that boundary can actually create more lift to create more storms kind of downstream. And these are typically in your summer months when you get the daytime heating, they pop up during the day, that sort of thing. Now your severe storms tend to fall into these categories: squall lines to supercell thunderstorms. And squall lines can go, they can extend hundreds of miles. Your supercell storms, these are single cell thunderstorms, but these are what I call they are the king of thunderstorms. These are the most powerful thunderstorms here in the world, those supercells. And kind of here's what they look like on radar. You know, we've got a squall line here that extends all the way from Indiana all the way back into southeast Oklahoma. And a supercell is a smaller storm on scale, but it is very violent. You may know what a hook echo is or something like that. So typically with a supercell, what separates that from another thunderstorm is that it's rotating. So you have a rotating updraft portion of the storm. Your tornado would be down here. Your heavy rain and hail is going to be up in this area right in here. And that's the supercell from the Tuscaloosa, Alabama tornado. So ingredients needed for storms. Anybody have any idea of what do we need for severe storms to develop? What are some of the things that we look for?
Cold air and hot mass running together?
That helps, yep. You have a boundary, something that can provide some lift to get those thunderstorms to develop. Sometimes that is a cold front. It kind of goes two ways. You can have a cold front with a boundary that kind of provides the lift, but you also need to have some cooler air aloft, which makes the atmosphere unstable, kind of warm and humid underneath, and the atmosphere unstable because you got cooler air aloft. We'll talk a little bit more about why that's the case here in just a second. But there are a lot of things that need to come together. We talked about the instability. Kind of think of a hot air balloon. The reason a hot air balloon rises because the air inside the balloon is warmer than the air around it. That's exactly why a thunderstorm rises. That thunderstorm is billowing up through the atmosphere once it gets past a certain point simply because it's warmer than the surrounding air. The greater the difference between that air of the thunderstorm and the surrounding atmosphere, the faster that updraft is going to rise. So that's instability. Moisture, typically in eastern Oklahoma, we look for about 55-degree dew points or higher. You go into western Oklahoma, where you got higher terrain, even out into the high plains of West Texas and eastern Colorado. Sometimes you can get away with a 45 to 50-degree dew point. A couple of years ago, witnessed a tornado way out west in the Oklahoma Panhandle. The dew point was 49 degrees, so it wasn't extremely humid air, which is pretty incredible. Some sort of lifting mechanism. We talked about the front, maybe a cold front, sometimes a dry line which separates dry air from the west and humid air to the east. In the case of a sea breeze like Florida, you get the cooler air that comes in off the ocean in the afternoon, and that acts like a little bit of a front, can raise the air, outflow boundaries from existing storms, forcing to rise to create other thunderstorms. The crucial one for tornadoes is wind shear. That is why some thunderstorms will produce tornadoes and why some of them will not. This is the big one right here. And I'll explain it. Let me I've got an umbrella here. So wind shear is the change of wind direction and speed as you go higher into the atmosphere. I'll go one forward. Typically what happens on a typical severe weather setup for Oklahoma, at the surface, I'll forget this later, we've got very warm, humid Gulf of Mexico air flowing up right off the Gulf of Mexico, right into Oklahoma. So at the surface where we are, we wake up in the morning, you can feel it. It's kind of warm, it's kind of muggy. Usually the wind's up, coming out of the south, you're getting that strong flow coming right out. As you go up with height, the wind direction is going to change direction, become more southwesterly, or even westerly. So it's that turning with height, and it gets stronger as you go with height, that gets the atmosphere to kind of roll horizontally. So my hand here, we got strong surface wind coming up from the Gulf of Mexico. Aloft, we got winds coming in this direction, and so you get this kind of horizontal roll to the air. You don't see this happening, but it's happening. So now what you need to have happen to get that vertical is basically a thunderstorm pop up. So it's rolling, and then a thunderstorm develops, and you get a strong updraft, and all of a sudden, that horizontal roll goes vertical, and now you've got a supercell thunderstorm rotating updraft. That is the difference when we look for tornadoes compared to just your average thunderstorms that may not have that wind shear. But with us, typically, Again, you got that warm, humid air at the surface. Just you wake up and boy, it feels like severe weather. You got a dry line out to the west, and that can position itself, depending on the day. Sometimes it makes it all the way to I-35. We've had it all the way to Tulsa before. In the day of the Joplin tornado, the dry line came almost all the way to Tulsa. But typically, that's the boundary between very warm and humid air and this desert dry air to the west. Out ahead of that dry line, sometimes temperatures 80 to 85 degrees. You get behind that dry line, it can be as much as 95 to 100 degrees. So it's just that boundary that helps provide a little bit of lift. Typically, we have a very similar upper level flow to what we've got right now. So as you go up with height, we kind of have this pattern set up right now, believe it or not. And we'll take a look at that. There actually is a severe weather threat down here, which we can look at later. But a trough in the west with the upper level winds kind of comes, digs across California and Arizona, and it kind of lifts out through the plains. That is a typical severe weather setup. And we just talked about this earlier, why the air rises within a thunderstorm. Again, strong billowing updraft here with this supercell, which was southwest of El Reno a few years ago. I snapped this picture, and it did go on to produce a tornado. But again, the air inside this thunderstorm is warmer than the air out here. So it's just going to keep going and going and going. And that is the measure of instability. It's kind of graphically here. That might be a little tough to understand, but this is basically the gist of it right here. And there's ways to measure this with weather balloons. Weather balloons are launched at different locations across the country two times a day. Now, sometimes they'll launch special balloons if there's a severe weather setup or something like that. But they measure temperature, moisture, wind speed, wind direction, and air pressure as you go up with height, because we know what the weather is down here, but what's happening above our heads is crucial as well to what kind of weather we could see. So this is kind of a skew-T diagram, and I'll try to make this as understandable as possible, but basically this line over here is the temperature. Sorry, I gotta get this here. The temperature, the actual temperature of the atmosphere as the weather balloon goes up. Now, once air reaches saturation, as it rises, it's going to cool at a different rate compared to when it's dry. So if we place a thunderstorm there, this is what the implied temperature might be, but it could be if we had a thunderstorm. And so as long as this stays warmer than that, which it is, the thunderstorm will keep rising up until this point when it hits the equilibrium level. Once you get way up in the atmosphere, the temperature actually will kind of, the drop off the actual atmosphere once you get closer to space kind of levels off. So as the thunderstorm builds up, it eventually hits a point where it's no longer warmer than the air around it, and that's where you'll hit the top of the storm. So there's our equilibrium level. That's where the amble is. And because these updrafts can be so violent, rising at 100 plus miles an hour, you'll get what you call an overshooting top on some of your strongest storms that actually kind of push the layers here going into space. We're talking 12, 13 miles up into the sky. It's incredible. And then there's your updraft. Your wall cloud and tornado is going to be in the updraft portion of the storm. Your heavy rain, hail, and all that will be more down here where the air is coming down out of the storm. Here's a time lapse. Again, you can watch some of these thunderstorms develop as they billow up through the sky. And you can see these updrafts here billowing up. You can watch them. See them build up, boom, boom, boom. So again, they're rising through the atmosphere. There you go. And the wind shear also helps as well, helps sustain the storms. So if you didn't have a lot of change in the wind speed with height, the thunderstorm would almost develop vertically. So it'll develop, but then once the rain starts falling, the rain will come right down through the updraft and it chokes itself out. So this is more common in the summer when we don't have quite as much strong upper level support. The winds are weaker aloft. In a sheared environment, as the thunderstorm billows up, it actually will go diagonally because the winds aloft are stronger. It's pushing the updraft forward as it goes up. This allows the storm to sustain itself. So the updraft does not get choked off. the rain and precipitation falls over here, the downdraft, and you still have this warm flow able to flow up into the updraft portion of the storm. So that's another reason why when you have a strong sheared environment, while that is conducive for severe storms, allows these storms to sustain themselves, this would be more of a summertime stuff. Now sometimes you can get a strong downburst as the thunderstorm collapses. You can still get some wind damage out of something like this. This is going to be more sustained, something more typical that we would see in the spring months. And again, kind of the look here, schematic of a supercell thunderstorm. We have the rotating updraft, strong inflow coming in here to the storm, that really warm inflow. And then aloft, very strong winds aloft, overshooting top, got your anvil. And looking down on it, this is kind of what it looks like. Warm, humid air flowing into the storm, kind of goes up into the storm, and then all the rain and cool air comes out over here. So it's kind of like its own engine. As long as this area here doesn't get cut off, and that warm air can continue to flow in the updraft, it'll just keep going. Sometimes though, that rear flank downdraft, which is cool, can cut off that inflow, and that usually will mean the death of the storm. And here's a low precipitation supercell. There's different types of supercells. You've got low precipitation, which doesn't produce a lot of precipitation. Classic, which is going to be more producing your classic type tornadoes. And you have HP, which and a lot of times you get rain-wrapped tornadoes in, so they have a lot more precipitation with them. But you can kind of see the structure here. This is a short time lapse, and I may play it more than once. You can see the updraft here is rotating. So your warm air is coming in here. It's rotating as it goes up. Now, it eventually got choked off right here by the downdraft, and that pretty much killed the storm. But we'll do this again. This produced 1-inch hail. Wasn't, again, it's a low precipitation supercell. Didn't produce a lot of precipitation. They did produce 1-inch hail in Tulsa, out over here, where the precipitation was falling over here. Clean look here at the updraft. You can clearly see it rotating. This was the same day as the Sand Springs tornado, by the way. Later, another storm came in and produced the Sand Springs tornado. Storm spotting and chasing. All right, we'll get into a little bit about what to look for and what you can look for as storms kind of come in. So there's a lot of different features that storms produce. Shelf cloud, which a lot of times gets confused with a wall cloud, and a wall cloud. Shelf cloud, it's going to be something that, I mean, it just goes, sometimes it goes as far as the eye can see. It can be menacing. I mean, it's like, oh my gosh, it's the end of the world coming at us here. But this is an indicator of straight line winds. So what's happening here, we've got a line of thunderstorms. The predominant flow with this type of thunderstorm is going to be outflow. So the air is rushing out of the storm, cool air is bumping in to the warm air in place, and you get this incredible cloud feature ahead of it. Now, as this comes over, the wind's going to pick up, eventually the rain will pick up, and the storm moves in. Wall cloud is actually a very small thing. It's not that big. This was near Protection, Kansas. This is more than several years ago. This right here, that little thing right there is a wall cloud. There's the base of our supercell right here. That little lowering, this is where the air is flowing up into it. Here's our RFD cut, our rear flank downdraft cut, where that air is kind of wrapping around right here, coming around. But right there, that's it. That's what everybody's watching. That's where the tornado would form. So wall clouds, they're not going to be this menacing, scary looking thing that comes in like a shelf cloud will be. They're typically smaller. And here's a shelf cloud. Sometimes you get these little fingers that come out. You might think they're tornadoes, but they're not. They might, and shelf clouds can be very turbulent. So a lot of times you can get little, what look like circulations in these things, but it's just more because of the turbulent movement of the air. It's not organized circulation from an updraft like you would see with this wall cloud that was out near May, Oklahoma a few years ago. This thing was sustained, it lasted. I really thought this was going to tornado. Never did. That happens a lot. But sustained rotation for a good 30 or 40 minutes, but it never produced. Whereas this, you'll get these things, they're short-lived, And again, outflow dominated. As you're looking at this, the air is flowing out of the storm, and you can kind of see where the warm air is kind of coming up over that cool air that's coming out. This is all inflow dominated, so the warm air is getting pulled in and getting sucked up. When you're looking at a wall cloud, typically the wind is going to be at your back if you're in the right position. When you're looking at a shelf cloud, as it comes in, the wind is going to come at your face. So outflow and inflow, that's a big difference. And again, shelf cloud coming across Lake Michigan. And sometimes you get these little low hanging clouds, what we call scud clouds, that a lot of times they get reported as funnels and such, but not necessarily any organized rotation. They're just very, sometimes with thunderstorms you got a lot of moisture around, so you can get a lot of condensation low to the ground, but it doesn't necessarily mean that we have tornadoes or anything like that. There's a lot of lookalikes out there. And here's one here. Again, it's just some condensation. If we had video of this, you would see there was really no rotation in it. It's just kind of a low-hanging cloud. And then on this one, this was actually underneath a shelf cloud as it was coming over. And what was happening here, if I can get the sharp thing to work here, the warm air was kind of hitting that, was kind of like buffering up against the cool air, and we actually had a little condensation where that was happening. And so you got this little cloud that kind of developed on the leading edge of that cooler outflow coming in. So there's a lot of things out there that might look like tornadoes, but they are not. This was Pawnee County, wall cloud right here. This is our rain-free base. All the rain and the hail's over here. Weak little wall cloud. This thing didn't really do anything. This was down in Fuskin County. This really didn't do anything at all.
That certainly qualifies a wall cloud right there.
So we just saw that form. Sometimes with the wall cloud, you'll notice that it kind of tilts down toward where the rain is. This was in Wagner County a few years ago. You can see the tail cloud coming into the wall cloud right there. Texas Panhandle, now a little bit more rotation in this. You can see it rotating right here. This did go on to produce a tornado about 5 minutes after this video was recorded. But good rotating wall cloud right there. Now, not all wall clouds are rotating, but once they start rotating.
And did you notice it started picking up?
That's when
when the rain started wrapping around the backside here.
So this is our rain-free base right here. All the hail and all that stuff's up over this area.
I can feel the strong inflow.
Southwest of Fort Cobb. You see wrapping up. You see a little funnel that's going to form here. But again, we're underneath. This is the rain-free updraft. All the rain and the hail is up over in this area. So here's our wall cloud. We actually get a few circulations here, right there. So we don't have a full condensation down to the ground, but we've got circulation down to the ground here. And this guy's going to lose his garage right there. You can see that it flies over the road. Yeah, there's our wall cloud right here. Again, it's not a big feature. It's not something that's going to be really scream out at you like, oh my gosh. So you can see it rotating right here. And it did. This is what eventually came out of it.
Wow!
This supercell, this was an incredible day. We got a new wall cloud forming here. This is what we call a cyclic supercell. So it's producing circulation after circulation. This produced about 12 tornadoes in about 2.5 hours.
Oh my God.
So that one's roping out, and as soon as that old circulation kind of dies out, the camera's going to pan here to the right, and you'll see a new wall cloud forming, and it produces another tornado.
Just like that.
So that one just roped out. It's amazing how quick it's gone. And then now pan here, look at this, another one about ready to go.
Oh my gosh.
One of the most dangerous things when chasing
Let's go into town.
other chasers. It is a nightmare out there.
We're in the heart of Cherokee right now, and we got a tornado due north of town.
mistake I made a few years ago, 2012, when I mentioned about HP supercells, rain-wrapped type tornadoes. We lost radar data. We were way out in southwest Oklahoma. Didn't have radar, didn't have any alerts coming in. We thought the storm was pretty much over with. So we're just kind of waiting to go home, and I kind of drove up into where the circulation might be, and I was more concerned with hail. And little did I know, we almost drove right into a tornado here. So I will never, ever mess with an HP supercell again. Honestly, I'll show you a video of the El Reno tornado here in a second. I think because of this, probably saved us in the El Reno tornado.
Holy crap.
Sorry for the language. So you can see the
back
back edge right here. Now this is actually pretty weak, but it kind of cut us off guard. You'll start to see a little bit of visible. And you can see the rain here, everything's getting sucked to it. So everything's getting pulled into this area here. And this is a widescreen camera that my buddy had, so we were closer than what it looks like, but not as close as that guy.
That guy's really close.
He's right next to it. So again, not a lot of, I mean, it's pretty weak, you can tell, and you can kind of see a little bit of movement in it, but not as much as you'll see in some of the more violent tornadoes. So here's what kind of this, what supercells look like on radar. And we're looking at 3 different supercells that went through Moore, Oklahoma and produced violent tornadoes in Moore, Oklahoma. We know May 3rd, and there's what it looked like. This was an EF4 that went through Moore on May 8th, 2003. And the far one on the right was the most recent one, the EF5 from May 20th of 2013. But you can see the structure of the storm. Now, radar data is getting a little bit better as we go through the years. But again, they all have that textbook hook here on the end. And again, your supercells are going to produce your higher end tornadoes. Sometimes you can get little spin ups within a line of storms, but your higher end tornadoes are going to come from supercells. So again, the path here across the south side of Oklahoma City kind of started down here near Newcastle, kind of went over 44, and tracked into Moore right down 4th, and then eventually lifted on the east side of Moore. And some of the more spectacular photos, one of the things that I was blown away with the power that this tornado had, 12-ton natural gas tank was carried a half mile and ended up in a residential area. So these things are quite powerful. If you remember the day before, we actually had violent tornadoes the day before around Shawnee, and a lot of times people forget about Shawnee and around the Luther area, the tornadoes that we had the day before the Moore tornado. So this is some of the data that we were looking at a couple days before they actually occurred. There are different computer models that we look at. This one was the GFS. 3 kilometer EHI is the Enhanced Helicity Index. It basically measures the shear that I was talking about in the lowest 3 kilometers of the atmosphere. So you can see the model is predicting here, if I can get this to work, there we go, pretty high EHI levels here in central Oklahoma, both on the 19th and the 20th, indicating that if we got thunderstorms to develop in that area, there's a pretty good chance that they will rotate. At the surface, our dew points and streamlines, so we've got high dew points here, 65 to 70 degree dew points. Again, that's a measure of the moisture in the air. That's the area you step outside, you're gonna feel it. I mean, it just feels muggy. Our CAPE, which is our instability, where I was talking about how thunderstorms are warmer than the outside air. And the bigger the difference, the faster that updraft is going to rise. That's our CAPE values right here, and they are pretty high as well. So we've got a lot of stuff coming together indicating that we could have severe weather on those 2 days. The morning of Moore tornado, SPC, the Storm Prediction Center, was highlighting an area here from southern portions of Missouri back into North Texas, included eastern Oklahoma and central Oklahoma, under moderate risk. The tornado outlook was hatched, and when they hatch it, they think that we could have tornadoes of greater than EF2. So if we get supercell storms, they could be strong tornadoes and not on the lower end of the scale. Our sounding, this was the actual sounding. This is not from a computer model, but this was a special sounding launched from Norman at noon, and this is what you call a loaded gun sounding. So at the surface, 81 degrees, 72 degree dew point, you go aloft, and the air gets drier and gets also cooler as well, which you can see here. But this is our dew point over here on the left, so it gets much drier. And then if a thunderstorm went up here, the thunderstorm temperature would be right about here. This is the actual temperature that the balloon measured. So we've got a big space here, a lot of cape right there. Notice our winds at the surface. We have a south wind as it goes up with height. Remember I was talking about that turning with height. As we go higher in the atmosphere, that wind becomes more southwest and eventually even almost westerly here. And I believe these are knots. I don't think they use miles per hour on this one. I believe these are knots. But as we start going up here, we're getting up here. Each one of these flags, the flag is a 50 knots. The longer line would be 10 knots and the shorter line would be 5 knots. So we're getting up here 60 knots or 65 knots. So we got stronger winds aloft, turning with height. Basically, this is called the loaded gun sounding because once a storm goes, it's like bang, it's going to go. Before tornado watches are issued, the Storm Prediction Center will actually issue a mesoscale discussion, kind of highlighting where they may issue a watch for later in the day. This was the mesoscale discussion that day, or the graphic where they were highlighting it. This was the actual tornado watch that was issued at 1:10 in the afternoon. On this day, let me go here, my video to load. May have locked up here a second. I've got the video here coming up. But on this day, you know, obviously we had a pretty high severe weather threat, not just in central Oklahoma, but also into parts of eastern Oklahoma. There we go. And this is a video I put together. Kind of shows some of the radar images and the timing of everything as it happens. And I'll show you. It's going to take a while here. It's a pretty long video. It's about 6 minutes. So hopefully, oh, it went forward one. Oh, actually, I'll go back and show you. I'll show you this first. This was our location here. We sat here the whole time. This is where the tornado tracked through. So we originally went south before the Moore storm had developed. We went south to target another storm. That one had weakened, so that's why we came up north. We saw the Moore storm developing, and we parked ourselves here right about at Indian Hills Road and I-35. Let's see if I can get there. So here's this radar image from the Norman radar, getting a little hook to develop here. There's more. Looking at this, we are about right in this area here, and the tornado just starts to form here. There it is right there.
Wow.
So at this point, it's still way out to our west. It's still way out. We're on I-35. It's crossing I-44 right now. So it's way out west at this point. We had a really good view.
Large stovepipe tornado on the ground.
Just before 3 o'clock.
You see, look at the inflow here. The inflow clouds
Tail
very
clouds going right into the
extremely
circulation.
organized.
There's our rain-free base. All the hail and most of the heavier rains up here.
I don't know if you can hear the wind through my
There's a little bit of
phone.
rain wrap here.
The
It's
air
tough to
is
see.
just- The inflow has just increased, probably
It's
about
right
10
in
to
there.
15 miles from what we have seen earlier. So the air is just being sucked into this storm, and it just looks like it's getting more violent as we have progressed here over the last 5 minutes or so.
Now it really starts to pick up here. Yeah, at this point, we start to realize that we've got a really bad situation on our hands. You can see the debris flying around there.
In the path of this tornado, right now is the time to take cover. Do not wait.
some of the violent tornadoes, you won't just get the horizontal motion, notice the vertical motion on the back side of it. I mean, it is really sucking the air. So this is actually my camera, not my buddy's camera. But as I was talking back to the station, I managed to grab my camera and kind of get a clip here myself. But again, look at on the back side here, look at the rising motion. I mean, this thing is just sucking. It's not just horizontal air, but it's like a vacuum cleaner going over. And sometimes you can get these horizontal vortices and rolls because the area is rising so fast. You can get these, some violent tornadoes, you can get these little horizontal vortices that show up.
Debris continues to fly in and around the circulation, and still, as mentioned, James, this thing is showing no signs of weakening. Oh, we can start to hear, you can hear it now, James. You can really hear the roar of the tornado now.
I wish that the sound would come
chasing
through.
tornadoes for many years, and this is one of the most violent I have ever witnessed.
It sounded like being next to like a thundering waterfall, like a Niagara Falls type thing. We thought we were about 1.5 miles away. When you go back and look at the path, it's about 2.5, 3 miles away. Yeah. So I'm on the phone. I'm talking to James and everybody back at the station with what's happening. So the rain starts wrapping around here. My video call is not showing up too well here, but you start losing. Where we start losing visibility is that you start losing visibility of is across I-35 because the rain kind of started wrapping around the back side of it. Vaughn Casher now chases from Channel 6. He used to chase with us. He's a good friend of mine. He set up east of Moore. He actually got it as it roped out, which you'll see here in a second. We lost visibility at this point. We got stuck in traffic. He's now at Channel 6, but I'll throw him up there. He was with us at the time.
We're going to get to another neighborhood.
So this is Vaughn's video
right
here.
now, if it is where we
So you
think
can
it
kind of
is,
see the
it's
tornadoes
in,
right here.
you know, some
It's kind of the wall cloud area. So he gets it as it ropes out here. And tornadoes go through different stages. You have your first forms, and you go through the mature stage, and then their final stage is when they
Extreme up. It's a huge cone still making its way, probably right down 4th Street. It's what I am 1 mile south of 4th, and I am on Douglas Boulevard, 1 mile south of 4th Street. It is a huge tornado still making its way. If you're obscured by the rain, don't be fooled by it. Take cover.
So right before it gets to Lake Stanley Draper.
Yeah, it's roping out. It's roping
out.
out. Right now, it's in its final stages. I don't know if there's another circulation developing, but this one right now is roping out. Thank goodness. I've got 1 mile west of me, and it's about a half a mile north of me. Just a beautiful rope coming out, and I'm glad it's roping out right now, James. But it's still got a lot of circulation.
So there's circulation going on here, but it's just not condensed. So I'll go ahead and move past that. And with the El Reno Day, that was quite a wild stretch we had in Oklahoma there in late May of 2013. We had more. We had the Shawnee and stuff, and we had tornadoes even around the day before El Reno. One that even hit Broken Arrow. So this was
a bell bottom type up.
there's our base of the supercell here, west of El Reno.
And James, the other thing that we're noticing, the winds here right now are due east in El Reno. The
Easterly winds taking the flag here. I mean, the air is literally getting sucked into the
flags are
storm.
basically being outstretched.
If the storm wasn't there, the wind would probably be out of the south to southeast.
Okay, we do have Michael
Right
Seger
there.
on the phone close to El Reno, and let's check in with Michael Seger. Michael, what have you got?
All right, we are looking at an
So
HP
our base is
supercell,
right here.
high-precipitation supercell, James.
A lot of rain wrapping around, so we're having a tough time seeing what's going on.
This is an extremely violent supercell, lightning in and around now the base of this storm.
So it's
And I
in
tell you
here
what,
somewhere.
the inflow is probably
You can
what,
see the
50
inflow,
miles an hour
I mean, it
right
is
now.
sucking.
And
Some of the strongest
I think
inflow I've
I'm gonna
ever felt.
Turn around and head a little south. We are due east now, probably by about what? Oh yeah, the hook. I'm looking at the radar on my phone here. The hook now is probably only about 2 miles away from us and coming at us. So we're going to do a quick turnaround and head a little farther south on 81. This is an extremely violent storm, and from our vantage point, we can't. It's so HP. High precipitation, it's rain wrapped. That's basically what I'm saying. It's rain wrapped, and we just can't get a good view of what's in there. But I imagine we're getting reports that there's possibly a tornado in there, but we just can't see it right now, and it's just too dangerous. We're going to head a little farther south.
I didn't want to get close to
See if
it.
you can see anything in there, guys.
So I'm driving.
God, it's really. Where at?
And I do bleep out a curse word here in a second.
Oh, look at the rain curtain dropped around. Oh yeah, that is it. Yeah, that's it. It's huge. Yeah.
So we're seeing that, and then kind of looking with the way the radar looked, we got out of there.
Right on top of us.
About a mile away, you can see that everything kind of whipping through here. And we thought it was coming at us at this point.
Yeah, we need to get. Yeah,
Ended up making its turn.
Holy sh! We need to get.
Sorry.
out of here.
I apologize for that. When it kind of hits you, and you realize the danger that you're in, sometimes stuff comes out. So we decided to just get south and get out of there.
On the ground over there.
The tornado's on the ground over here.
See that? Yeah.
But it made a turn back to the north and east, and that's what caught a lot of chasers off guard.
We couldn't see because it got so.
We went south and ended up going farther away from us, so it's way up here.
Holy crap! Oh yeah, it's wrapped like ridiculous.
So there it is. It's just a mass on the ground. But this caught a lot of chasers off guard. Unfortunately, we lost 3 well-renowned chasers, and one of the guys behind a lot of severe weather research that day, Tim Samarison and his son, and then one of their chase buddies as well. And we also lost an amateur chaser that day as well. And that's the only time, or the first time that I know of where a tornado actually killed chasers. So that was kind of a sobering day, and a lot of other chasers were very lucky. I don't know if you've seen this clip. I know I've showed this in years past of the Weather Channel crew getting hit. Now the Weather Channel was behind us. We got out of there before they did.
Right there. We could be putting ourselves in a dangerous position here, and we're going to roll just to stay safe, okay?
And meteorologist Mike Bettis could not have been more accurate. Bettis and 5 other experienced chasers.
So they're on 81, which is where we were, but we were farther south than they were.
This circulation appeared to have gone almost right over Mike Bettis, so that we're concerned for their safety.
Despite their best efforts to outrun this violent tornado, near El Reno, Oklahoma, Twister overtook their fleet of 3 chase vehicles. Bettis says their car was thrown at least 200 yards.
So you can see, and I'll talk about this in a second.
Keep going again. Everybody come down. Everybody come down.
Now the camera keeps rolling, and it gets their vehicle rolling away. Watch this.
Amazingly, photographer Brad Reynolds was able
Right there.
to keep the camera rolling and capture this dramatic video from
So the
inside
camera's
the
on its
car.
side, you're watching their vehicle
We tumbled, I don't know.
roll through the field.
I would count at least 6, 8 times. We tumbled, and then we were airborne at one point. We were just floating, and we weren't tumbling anymore, and then we came down hard.
It's estimated this tornado was more than a mile wide, with winds upwards of 120 miles per hour. The main vehicle took the brunt with 3 of the team in that car.
That was, otherwise getting that many right there every time we get tornado chasing. That was a dangerous situation out there.
Looking at the tornado and the vehicle, the crew admits it's amazing. Everyone was able to walk away. and everyone was bruised.
You can see the little vortices that are inside it.
And yes, while the crew is banged up and bruised, they are all doing okay. And in a statement from the Weather Channel, we are aware just how unpredictable tornadoes can be, and everyone at the Weather Channel is grateful for our friends and colleagues.
Just let me say this, we're in the time of day. You know, we were trying to get out of the storm, trying to do the right thing and get outside of it, get away from it, and it just we just didn't have time to react, and
Important reminder for all of us to take these warnings seriously. I'm meteorologist Todd Santos.
So yeah, that was a kind of a unique situation. Remember I had talked about before with the HP, what caught a lot of chasers off guard, including us, is typically with an HP supercell, you've got a lot of rain wrapping around, and the tornado is somewhere inside that rain. But you really don't think that the whole thing is the tornado, which is what ended up being the case with the El Reno tornado, is a lot of people, including myself initially, thought we just had rain wrapping around perhaps a smaller tornado inside. But the whole circulation became the tornado itself, and then there was a bunch of other little tornadoes inside that. It was a very unusual storm. A lot of researchers got some great data on it, but winds were close to about 300 miles per hour in some of those smaller vortices. So what was happening is you had the main circulation rotating about 120 to 140 miles per hour, and then you had other tinier circulations within that were rotating about 160 miles per hour. So when you do the math, if you got that circulation and another one in there on part of that area, you're gonna add that together, you're gonna be close to 300 miles an hour. And so what you saw there in their video with some of those littler circulations that would actually pick them up and through them. But that's my actual presentation. Now, if you want, we've actually got some active weather out there right now. Do you want to pull up some data and take a look at it? Anybody want to do that? Let me close this out.
You missed a tornado warning by about 10 minutes.
Oh, is that right? Where was it at?
Just on the other side of the Oklahoma border in Arkansas.
In
near
Arkansas?
Seger Creek.
Ooh. All right, well, we'll pull up some of this stuff here then. Let me pull up. Bring our scope up. So we'll take a look at radar here, and then I'll kind of show you, we'll take a look at some data and kind of show you why we're getting some storms. So it's kind of a fun day here. But you know what, I need to put my Wi-Fi. That would help. Close that. Let's get to there we go. On the back edge now here. It's crazy how dry we were. Pattern changed.
Yeah.
They always say it takes a flood to end a drought. Parts of southeast Oklahoma had over 10 inches last week. It's taking a little while maybe for some of the warnings here.
Yeah, I didn't have any warnings up currently.
Okay.
Just got a tornado watch for central Arkansas, far southeast Oklahoma, and northern Texas.
Okay. We'll zoom out here, goes one way. So there's our storms. Let me pull up. Let's see. Chrome here. So we're starting to get that time of year. A lot of times late February, early March, the setups tend to go a little bit farther east, which is what we've got today. And there's a reason behind that. We get a lot of fronts that come in from the west and the northwest, and it'll push the Gulf of Mexico moisture well east. That Gulf of Mexico moisture tries to return back to Oklahoma, but before it has a chance, the next system comes in. But it has a little easier chance to return that warm Gulf of Mexico moisture to the east of us this time of year. But it can happen, you know, we can get stuff this time of year as well. But a lot of times you'll see this where it sets up just east of us, and especially across the southern states into Dixie Alley. I need to get my applications. There we go. So we'll take a look at what we've got here, and I'll pull up some model data, and I'll kind of show you kind of how we forecast. Forecasting, it's not as hard as you think, but then it can be really tricky at times, depending on the setup. One of my favorite pages, and you can get this at home if you want to write this down, is the College of DuPage site. It's weather.cod.edu. And they have access to a lot of computer models. There are other computer models out there, like the European model, that you have to pay to have access to. Our station pays for it, so we have access to it. But all the American models are open for anybody to look at. So let's go ahead and I'll pull up SPC here as well. We can take a look at the watch itself. Again, Storm Prediction Center in Norman, they are in charge of the entire country as far as watches are concerned, tornado and severe thunderstorm watches. They are in charge of the entire country. So here's their outlook here. So they kind of highlighted, they've got the radar on here as well, but this was the area zone here that's been highlighted for severe weather today, from southern Indiana, Kentucky, and Tennessee, basically Mississippi River Valley back into Arkansas, and then kind of clipping here, far southeast Oklahoma. That red box right there, that's our tornado watch that was just issued. So there it is. And we can take a look at the text. There it is visually. Back that up. And so here we go. We'll take a look at the text here. So effective Saturday morning, 1 o'clock or 11 o'clock till 6 p.m. today. A few tornadoes likely with a couple intense tornadoes possible. Spreading damaging winds likely with isolated significant gusts to 75 miles per hour possible. Isolated very large hail events of 2 inches in diameter possible. So they're anticipating thunderstorms to up, which they already are, with a potential for supercells. Again, we talked about supercells. They will produce your higher end type severe weather. And then they kind of have an idea there where the watch is going to be. But let's pull up some first we'll take a look. They have their forecast page. I use this a lot when I'm chasing, the forecast tools page. And we can look at the mesoscale analysis here. So let's click on areas here. Now let's pull up, and it might be tough to see. Let's go, let's see if I can just get, somebody can just get duplicates. Surface observations, let's do that. So, all right, there's all of our thunderstorms, and you can see here across southern portions of Arkansas, we have 73 degrees. I believe that's a 68. Is that a 68? Yeah. Wow, that is a 68 degree dew point. So that's really humid and juicy air. So we've got a lot of warm and humid air here at the surface. And you can see the winds. There's our flags right here. They're all out of the south here. So this area right here, very, very juicy and warm and humid air. But again, that's just one ingredient that you look for. as we go up with height, let's look at, we'll look at 500 millibars. So now we're going to go up a little bit with height. So here's our trough, and our trough is kind of like a dip in the mid to upper level flow. So our trough is out here, you can see that, and then we go up in height, and now we've got winds aloft coming in out of the south and west. And we just looked at the surface, we had winds out of the south. Go up another 3 miles or so, and that wind now is out of the south and west, almost west-southwest. So everything is coming together here, at least as far as we get the shear going. I wonder, let's see. We're talking about the cape. This time of year it's tough to get really big cape. That's the instability that I was talking about. The bigger the difference between the temperature of the thunderstorm and the surrounding air, the measurement of that. So you can see here, 500, 1,000 joule. It's not great, but if you have strong enough shear, you don't really need a lot of cape, because the shear, that's the key ingredient for tornadoes to get rotating updrafts. But you can see highlighted in this zone here, the capes are not great, but again, it's tough to get really high cape this time of year because we just don't get the heating, but certainly sufficient. Now when we get to late spring, sometimes we get capes 4,000, 5,000 joules per kilogram. It gets really unstable with an updraft. It'll go like a rocket through the atmosphere. So let's take a look here at wind shear. There's a few ways to measure it. I like looking at storm relative helicity from surface to 1 kilometer, so the lowest kilometer, 0.6 miles of the atmosphere, because that's where the tornado is going to form. So you want a lot of, if you're chasing, you don't want a lot, because if you get a tornado you can do damage, but as far as for tornadoes, you need a lot of low level shear, and this is plenty sufficient. We've got, typically you look at 150 to 250 as being good enough. We've got numbers here. We're way up. We're getting about 250, 300. Now this could be a little bit deceiving here with the 600 in southeast Oklahoma. Sometimes when you have that shallow layer of cold air in place, sometimes you get really strong wind shear, but nothing, the other stuff is not coming together. But where we have that overlay with unstable air and that warm, humid air, and overlaid on top of that high level, low level shear, that zone in here certainly would be worth watching. So if I'm not chasing because this is real-time data, we're not looking at like out in the future like you do with forecast models. So this is how it is right now, and it's estimated. It's not perfect, but it kind of gives you an idea of where certain zones might be setting up to where conditions might be more favorable for storms. And what I'll do here, let me pull up some model data. And let's go. We'll look at this morning's NAM. And computer models work. It's unbelievable. People that are way smarter than me, it's basically physics. It is what you call atmospheric dynamics, which is a bunch of physics. How it works is they map the Earth in a computer, and they've got everything from lakes, and some of these high resolution models on there, they've got lakes, all that stuff is in their elevation. When weather balloons are launched at different locations across the Earth, that data is put in to these computer models. Planes get data, ships get data out at sea, because obviously we don't have a lot of surface data out at sea. And all that gets thrown in, and it's not going to be perfect, but it's pretty darn good how it works. So what happens is all that data gets thrown in, and you basically push play, and it's calculating, millions of calculations. This air is moving this way, that's going to move this way, that's going to move this way, and it just plays out the atmosphere in the future. It's unbelievable how it works. And the process takes hours. especially with some of these the higher resolution model will come. They only go out so far because it would take so much longer to go out, you know, a week plus in advance. The lower resolution models will go out farther into the future, but just because of the time it takes to calculate. This particular model takes almost 3 hours to come in. So it ran at 6 o'clock this morning. We usually start getting in the 12Z data at around you know, a little before 9 o'clock in the morning. But this is what it's actually trying to predict the radar may look like. And again, it's not going to be perfect, but it does a pretty good job most of the time, not always. But you can see the line of storms here. One thing that I'm looking at here, it's very messy as far as there's a lot of storms around, and sometimes that can actually weaken storms, so it prevents them from being out there isolated by themselves. Let's see, where we at? We're at 22Z. So pretty good line, and with that, we looked at the shear values that were out ahead of this, so as this line comes in, we may actually end up getting little circulations develop within the line of storms. Now those typically tend to be weaker than a supercell, but sometimes you can get little spinouts within a line if everything lines up just right. We saw one of those just in August in Tulsa last year. All right, let's look at some actual severe weather stuff here. I want to look at this one. Convective prop. So this is the 12Z NAM. So this one ran at 6 o'clock this morning. And so this is what the computer model is thinking. Let me zoom in the view here. And I'm sorry some of this kind of goes, if you're not understanding some of this, I hope you're kind of getting the gist of it though, kind of with some of the stuff that we're looking at. Let's look at, so here's our computer model, again, that we're at 12Z, which is Zulu time, which is 6 o'clock in the morning our time. So we're going to go out in the future here. 18Z would be noon, and we're looking at that low shear. So we're looking for the 0 to 1 kilometer shear, where those values are going to be highest. So we go into the afternoon, and you can see here, very high levels. The model is thinking very high levels here across eastern Arkansas, into the Mississippi River Valley, maybe even all the way up into southern Indiana. And so very high levels of low level shear mixed in here. And we can also look, let me click on back one. Let me click on a sounding, we'll just take it right there, 40. What I like about this is you can also look at what the sounding may look like. So it's going to load here in a second. There we go. Not a lot of cape. Very skinny cape. Remember the more sounding that I showed you, where this was way out here, we had a lot more space between the actual temperature of the atmosphere and what the thunderstorm temperature might be. So, but not a lot, but sufficient. Fairly saturated through the level. We don't have a lot of dry air or loft. There might actually be, depending on what the model indicates, we might actually have a thunderstorm here at the moment, what the model thinks. But a few things to look at here. Remember I showed you with more south wind at the surface. As we go up with height, look how the winds really turn. We call that veering winds with height. And much stronger winds aloft. I mean, these thunderstorms are going to race. Your steering currents, what really drive the thunderstorms and push them along, are going to be right in this area here. I mean, these thunderstorms are these are probably going to be moving 55, 60 miles an hour probably. These are going to be racing. But we got that turning. What we also look at is what we call the hodograph. And this curve right here is in the lowest kilometer of the atmosphere. That is about as textbook as you see for tornadoes. So we've got a really good curve. Again, that's kind of indicated here as well. Just looking at this, you can kind of see that turning of the winds with height. They're pointing up, so that means a south wind. These are going this direction, so that means the wind's going that way as you go up with height. So very strong winds aloft. Strong winds as you go up with height, that's a higher shear. And we don't have a lot of cape, but this time of year, really don't need a lot of cape. Typically, as we go through the spring, we tend to get bigger instability. But that's pretty good. You can see it actually has an algorithm. I don't know if you can see it there. It's triggered and it says tornado. But these are some of the things we look at when it comes to severe weather. Let me go here. Let's go 300 millibars. I'm going to actually zoom out. Let me take a different view if I can. I'll do it on the model. We'll look at it on the model. Let me zoom out, change my view. Continental US, and let's go 250 millibars. Just look at the wind speed. So what we've got here, this is our jet stream. So now we're way up in the atmosphere, upper levels of the atmosphere, the wind flow. We've actually got a little split flow here. The northern jet kind of coming down through here. Did you see it snowed in Vegas yesterday? Anybody see that? It's a lot of cold air coming in across the west. They've had record highs in the east. So a lot of times when you get record, especially if there's records in the east, it's going to be abnormally cold in the west because you get a big trough and then you get the ridge, kind of the jet stream digging down, and then it goes this way. We've been kind of stuck in between. The subtropical jet, very strong winds coming in. Look at these winds here. I'm trying to look at the bars. Let me just put my stuff to read on there. Yeah, we're looking 145, 147, 150 knots. Well, if you were taking a flight from Mexico to Little Rock, you could be there in no time. Actually, I was in Denver at the storm chasing conference last weekend, and we made it to Tulsa in just a little over an hour. The jet stream was kind of coming down like this, and we just rode the jet. We were here in no time. So yeah, we got really strong winds aloft. So yeah, that's one of the things you look at. We call it jet streak right here. And a lot of times in the exit regions here where these strong jet streaks, you can get a lot of lift. So kind of look for these where the jet streak kind of starts to slow down here. But yeah, big trough in the west. A lot of times in severe weather season, we start to see this pattern of trough in the west and then kind of lifting out of the south and west and going like that. And we know that we're going to have a pretty good chance of seeing severe weather. And that's one of the reasons why, you know, I-44 is like, oh, storms always seem to follow I-44. You know, why is that the case? Well, basically because for a really typical strong severe weather setup, the steering currents of the atmosphere are going to be going from southwest to north and east. So what drives the storms in that direction are going to be going that direction. That's not always the case. Sometimes we get westerly flow to really steer those storms more west to east, and rare occasions, it does happen on occasion here, more so you'll see it up north, but occasionally maybe a northwest to southeast moving. Now in the late spring and in the summer, when we get what we call northwest flow, where the jet's kind of coming down like this from the Rockies, what will happen is storms will develop in the high plains of the Rockies, and they'll ride the jet stream down over us, and they usually get here overnight into the early morning hours, what we call these little NCS complexes that come in. We get this a lot in June, these overnight thunderstorm complexes that come rolling in, or they get here early in the morning. A lot of times what's happening is we get the jet streams coming in out of this direction, the storms go up over the high plains, and then they get here kind of the next day. Those can produce some straight line wind damage. You know, they can kind of bow out and arc out. But that's how we get a lot of our rain in June. But again, this southwest, if we were in April and May and we had this flow, I'd be very concerned, yeah. It's still a little early in the season for us. Typically, again, typically, it can happen anytime, but more often than not, this zone here, late winter and early spring is where the severe weather tends to happen, what we call Dixie Alley. And as we start to get a little more moisture available for us, as these systems come through and they kind of push the moisture away from us, the moisture tries to come back, but then the next one comes through before it has a chance. We start to get a little bit more moisture availability later in the spring. So when these systems do come through, then we have the moisture in place for severe weather. Does anybody have any questions? I'm just kind of talking on here. Yes?
I know, on the order it's always been considered for when I
Yes.
We haven't, the last few years, and you hear people surmise like, well, you know, we get hit in Illinois and Indiana and down in Mississippi and places, you know, they think, they might say, well, the weather patterns change. I kinda wonder if maybe if they didn't, maybe those places were always hit, but now we've got 24/7 news, so we're hearing about it.
What typically happens is, I grew up in southern Indiana, and it was Indiana's largest tornado outbreak. It was June 2nd, 1990, so it's the largest outbreak to this day. F4 at the time, since they updated the scale. Went about 20 miles from my house, and I remember going through seeing the damage. That's what really kind of got me interested. I mean, I was always kind of curious, but that was what really sparked it. But you know, a lot of the big outbreaks, you got the Palm Sunday outbreak, the super outbreak of '74, those hit areas here to the east. You tend to get a lot of big outbreaks east. We have a lot more days where we could see tornadoes. But tornadoes, there's Dixie Alley, we have what we call our typical tornado alley. There's actually a little area in Indiana called Hoosier Alley, where there's a little more tornado activity. But everybody in here gets tornadoes. What typically tends to happen is we tend to get a lot of big outbreaks in this part of the world. More so, I mean, we get big outbreaks here, but I'm talking large, large scale, going from, tornadoes from Ohio all the way down to Mississippi. Ours tend to be a little bit more concentrated. We typically don't see tornadoes going from South Dakota all the way back down to Texas, whereas sometimes in the east you get these massive outbreaks that just produce large number of tornadoes. So they occur everywhere. Again, frequency and per square mile, I still think central Oklahoma, basically I-35, probably is the capital of the world. No, I grew up going into the basement of our home, tornado warning in southern Indiana. It happens every year, so everybody gets them. But the frequency of getting supercell storms that, what we were just looking at here, the conditions that you need, that shear, they just happen a little bit more frequently in this part of the country than they do to the east, but they do happen to the east as well. I don't know if it helped answer your question or not, but.
Yeah.
Okay.
They've always happened in
Yes.
places we just didn't hear about.
Yeah, you've got, trying to think of some of the big ones that have happened to the east. You've got, your Xenia, Ohio, F5, which is north of the Cincinnati. That was in the '74 outbreak. So Dixie Alley, we've had a lot of big outbreaks across the southern states. Tuscaloosa got hit back in 2011, which is down there. That is actually the largest tornado outbreak in U.S. history. I think it's over, I can't remember the exact number, it's well over 200 tornadoes in a 24-hour period. But anybody else have any questions or anything? Yeah.
Well, I've heard, for years that you're supposed to get out of your car and get in the ditch. And on the actual Weather Channel, somebody, I don't remember who it was claiming now they're taking care of the airbags and stuff, that you're better off.
There is some talk, and it might have been, was it even during the Sand Springs tornado this came up, where somebody kind of took their car and went down low, took it off road. There's a lot of debate about doing that. I mean, I don't know, it's tough to say. You're gonna have to kind of make that conclusion when you're there yourself, what would be the best option. I always, if you can get away, get away. If you know there's enough time to do it, just try not to put yourself in a situation where you're so close you can't get away from it. If you get into that situation, if you are exposed and there's nowhere to go, I might risk getting out of the car and just trying to spread eagle and lay as far as I can in a low spot, because the car, if it's violent, the car might get taken. But it's a judgment call. But I know exactly what you're talking about, because there is some talk maybe staying in the car in certain situations might be a better option. So there is kind of a new debate that has come up with that. Yes. And everybody's going to have it's going to be a judgment call. When you're there, you're going to see the situation. where the tornado is it moving away from me, is it moving toward me, do I have time to get away? So it would have, you know, it's going to be a judgment call on your part. Certain situations, if you can get away, get out. If you can't, then bunker down. Anybody else have any other questions? I want to thank everybody for coming. I've been interested in the weather since I was, you know, yay high, and I just kind of touched base on it there. You know, I kind of grew up, you know, in rural southern Indiana. I had my bedroom window. I kind of set up on our house set up on a little bit of a hill, and my bedroom window faced west. And I was glued to that window so many times when storms would come rolling in from the west. I mean, I would lose sleep in the middle of the night. I'd be right there watching the storms coming in. So it's something I've been interested and fascinated in since I was a kid. You know, I did have a little bit of a fear at first growing up, but that fear turned into curiosity to like, especially, you know, I was talking about that outbreak, and when I first saw significant tornado damage was in Petersburg, Indiana, in 1990 with that F4, and I was 13 years old at the time, and I could not believe the power. Like, I was like, how in the world could something do this? You know, I mean, a solid brick home. Whoops, I just dropped that solid brick home, and just ripped to shreds. You know, and so it struck me. You know, and I became fascinated and curious, and I'm fortunate to kind of make a career out of it. But if you have any questions, feel free to, you can email me any questions you have or anything like that. It's just mseger@fox23.com. That's my email. It's spelled like Bob Seger, but it is pronounced Seger. So it's a German name. But if nobody else has any questions, or you want to say something talk to me, yeah, go ahead.
One more question.
Yeah.
In the old days, when I was a kid, they always told you to open your doors and windows to equalize the pressure.
Yep.
They don't ever say that.
No, and it's not. The reason it is pretty much the tornado is going to take care of that for you.
It's going to.
It's going to blow out the windows, and the idea was they used to think it was trying to equalize the pressure. That's actually not what's happening. What's happening is there's so much force and air being pushed into your home basically explodes like a balloon. So there's so much wind coming in that your house basically expands. And you'll see that a lot, like the roof lifts up. It's because the air is going in. There's also kind of a little bit of the force of the wind taking kind of the upper part of the roof, but a lot of it is the wind and the air getting basically crammed into your home and lifting it up.
So it's not a vacuum.
It is, well, the tornado itself is kind of like a vacuum,
Oh, okay.
but the force of the air being thrown into your home, the wind, it will increase the pressure of the inside of your house, and your house basically just kind of.
I'd always heard that, so I didn't know if
Yeah.
that's true or not.
And one of the things I did not touch base here, but and imagine taking a vacuum, like laying a bunch of glitter or whatever down, and just kind of taking the nose of your vacuum and kind of just holding it just above, and you'll watch the glitter get sucked toward the vacuum. That's basically what a tornado is doing. So the thunderstorm is the vacuum. The end of the hose is the tornado. And so when the storm drives the whole thing, and you've got a 12-mile tall thunderstorm, an updraft going at 100+ miles an hour, that tornado is small compared to the storm itself. And that's why I always tell everybody, I was like, can you do anything to stop a tornado? I was like, the tornado's along for the ride.
Yeah.
You know, the storm is the engine. The storm is driving everything. So wherever the storm goes, that's where the tornado's going to go. Now it may kind of meander a little bit along its way, but you got this giant thunderstorm going along. Tornado's just kind of hanging along for the ride. So there's, you know, a lot of people think Tulsa is safe, you know, because of the river. Although Tulsa's been hit numerous times in the last few years, but there's like this preconceived, like, oh, we're safe from tornadoes. Tornadoes never happen here. It's just a luck of the draw. So it just depends on where everything goes. You know, Joplin was hit with an EF5. Moore was hit with an EF5 within the last few years. What's right in between? So and it can happen. It can happen anywhere. Any other questions, or you want to come up and talk with me afterwards, feel free. So I'll hang out here for a little bit if anybody has any questions. And thank you again, John, for setting everything up. John, he's one of our storm trackers at Fox 23, does a great job with us. He's been with us for a couple of years. Provides us with great information, especially in this part of our area. You know, we like to have people all over because we cover such a large area. John has done a great job for us, and he's the one that was really kind of behind setting all this up. So I want to make sure to give thanks to John for doing that.
All right, everybody give Michael a hand for. I'm gonna have Survival Zone come up here and tell them a little about their safer and stuff just real quick. And then after that, whenever did anybody not sign in? You were late.
I'm just gonna keep it just a second, guys.
We're gonna give away a couple weather radios off of those. So while he's doing that, I'll get that ready. Come on, baby.
I'm just gonna tell you a little bit about our history. We're a somewhat local company. Our shop's located down between kind of Ramona and Oologah. Most of the guys that work for me is around Oshaleta. We've got a room sitting over here at Dewey on display, and we've put in lots of rooms up around Bartlesville. In fact, one of your local police officers just had one here recently. But anyway, we started back in 2004. We've wholesaled to other companies, mainly a guy out of Owasso for years, 13 years. We started our own company last year because we knew what everybody had out there, and we just out horsepower. We've got the only 3/8" thick room that's being built right now. This thing's like a tank. They tried everywhere in the world to dent it down at Texas Tech. We just come out with a new one. We don't have it on our information yet because we only had it tested last week. All of our rooms are FEMA, and meet or exceed FEMA guidelines. We tested a 1/4" room last week that we're coming out with. Just basically, it's going to be a basic room. It's a lot more affordable for people. That's something we've saw the last couple of years doing home shows. Is that, you know, there's some of them are just so expensive, and it's mainly for that and for builders. Maybe they'll start thinking about putting more of them in homes as builders. Anyway, if you guys got any questions for us or anything, I grew up in 1983. My grandmother. I lived just about 2.5 miles northeast of Collinsville. 1983, my grandmother lived there in a farmhouse for 50 years. And after my granddad died, they moved her into a mobile home. And one night at 11 o'clock, just before we had as much warnings like we got today, 11 o'clock a tornado comes in there and there was nothing left but the pumps. Okay. 1991, just about a 1/4 mile down the road where I live, my son back there was playing Little League in Oshaleta. And people were calling members of the team going, hey, you guys' houses are getting hit. And I lost about 25 palm trees, the roof off my house, my buildings. 2 houses right across the street got wiped out, and behind me got wiped out. It's either the year before or the year after one went right over us and wiped out Oologah High School. And they never did find some of those buses. But anyway, so I'm in something I feel like there's a great need for. Everybody needs to do something. Like, people say, what's better, this one or that one, in ground or something. You just need something, something to stay safe because they do a lot of damage. And if you guys got any questions or anything, I'd be glad to answer any questions you got. Okay? I'm just glad we got somebody with kind of knowledge Michael's got to help keep us safe. Give us some warnings,
Try. Well, thank you very much. Thank you.
All right, so I went to Walmart last night to get a weather radio. It turns out they don't have none. So whenever you signed your name, we put a ticket number by it. And I'm gonna have, since she has small hands, I'm gonna have her draw that.
Put her to work.
And then whenever I say your name, make sure to get with me so I can get your address. I'll have Amazon send it to you. So go ahead and pick out one. No, go ahead, hang on.
Grab a ticket, Eddie.
I forgot the clipboard.
Stick your hand in the jar.
Grab the ticket, remember I told you?
Oh.
Just one. Grab one. Great start of the show. Okay, hold it. Yeah, there you go.
So I put in all that work and then you took it from me.
Larry Maddox? All right. And then grab it, no, you need one more. Grab one more big one. Okay, grab that one.
See, when she
You never
gets too
affect
old,
anything.
then we'll have him getting it. Yeah.
Oh, forgive me if I mess this up. El Wando Build? Okay, alright. But, we appreciate y'all coming out. Mike will be here for a little bit, if you want to chit chat him.
Yeah,
We'll be
feel
over
free.
here in slow corner too, so, and I'll get you guys' information. Thank you again, Michael.
Thank you, John, appreciate it. Thank you everybody for coming.